Today we have we will start with a talk in cybersecurity. The day number 3 is cybersecurity. So we have a talk. Then we will have a hands-on session, and we will have a panel. Today, Dr. Elias Behar from the University of Texas at San Antonio will be leading the day. Dr. Behar is currently the Associate Director of the Cyber Center for Security and Analytics at UTSA, University of Texas, San Antonio, where he leads, co-directs, and co-organizes university-wide innovative cybersecurity research, development, and training initiatives. He's also an associate professor at the Department of Information Systems and Cybersecurity, specializing in operational cybersecurity and data science as applicable to national security challenges. Previously, he was a senior research scientist at Carnegie Mellon University, where he contributed to federal funded projects related to critical infrastructure security and worked closely with the Software Engineering Institute. His research and development activities and interests focus on operational cybersecurity, attacks detection and characterization, malware investigation, cybersecurity for critical infrastructure, and big data analytics. Dr. Behar is the co-principal investigator of this project that is funded this workshop. So welcome, Elias, and I will let you lead today's workshop.
Thank you, Jorge. Let me share quickly my screen. Are we good?
Yes.
Excellent. So again, Jorge and Jason and everyone from the panel side of things, thank you very much for this workshop. I know it's we've been having, everyone, the whole world is having tough times through this. So the fact that we're pulling this, especially on the hands-on aspects, I think this is a good effort. Although it's not ideal, but we're happy that we have many participants with us, and hopefully in this next iteration we will have we'll have a physical and see everyone hopefully. So today we have basically a talk about cybersecurity and measurements, and then I'll be talking about BRO and going through 2 labs related to BRO hands-on sessions provided by NDG and the developed labs, and then we'll have a break, and then we'll go through a panel where we'll have people from academia, industry, and the private and the public sector to discuss a few noteworthy questions. So to start today, I'm very, very happy to introduce to you Professor Nur Zincir-Heywood. She's a full professor at Dalhousie University in Canada in the computer science department. Professor Heywood has published extensively in lead security and networks and services venues. She's the associate editor of IEEE TNSM, and she did a lot of contribution throughout her career, and she continues to do that. I am honored to have Dr. Heywood. One thing that you should know that Dr. Heywood actually, back in 2015, she acted as my external PhD examiner. And when I was doing my master's and PhD, I read a lot of her papers and her group's papers. So I'm very delighted to have Dr. Heywood with us today. She will be giving a talk, and I will stop sharing my screen, Dr. Heywood, so you can share and you can proceed with your talk. Is this okay? So,
Elias, yes.
Yes, correct.
That was an excellent introduction. We will wait for Dr. Heywood for sharing the screen.
Yep. Nur, do you need any help with sharing the screen?
Dr. Heywood, no, we cannot hear you. Let me see if we...
I think might be...
Dr. Heywood, there is at the bottom of the screen.
Hold on, Jorge. She
okay.
dropped, so I need to promote her.
Okay.
Okay, Dr. Heywood, you should be able to unmute, and in the middle of your screen, there's a green button that should say Share Screen.
Yes, now I can see it. Before I couldn't see, and I was trying to talk to you all, but I think you weren't able to hear me. Let's try. How about now?
We can see that. Thank you, Dr. Heywood.
Thank you. And I'm very happy to be here with you all. And thank you for inviting me for this very interesting workshop. And hopefully next time I'll be able to see everyone face to face. Okay, so today I'm going to talk about some of the research I have been doing with my students at Dalhousie University, Faculty of Computer Science. Our research lab is called Network Information Management and Security Lab. So I'm very happy to share their work with you. My talk is about our experiences with trying to create cyber arm races for the good guys who is trying to keep the cybersecurity as best as we can. Okay, so in my lab, the idea is to work on interesting research problems, anything to do with cyber, I guess. I can say in a nutshell, but what we are looking at is different network-related, application-related, and service-related problems. And while we are looking at these problems, we are keeping in mind that we want to create systems as solutions that can adapt to the changing environment of networks, applications, and services. And our focus is mostly trying to identify the different behaviors in this ecosystem, in this changing environment of the cyber world. And in this workshop, I think since the beginning on Monday, very interesting topics are brought up, really interesting talks and hands-on sessions. And some of my students are attending and they are telling me they are enjoying it a lot too. So thanks to everyone before me. I'm sure it will continue this way, hopefully today as well. So what we've been looking at is high-speed networks, right? And which is very important to be able to create this this backbone for our world, for our cyber world. But in this cyber world, as we said, it's an ecosystem. There are many different devices that is connecting to this high-speed network. These are our smartphones to our desktops, laptops, and more the unmanned vehicles, Internet of anything that we can think of, including our fridges and digital photo frames. So in this world, trying to secure all these different elements of the ecosystem is not easy. And while we are trying to make sure the backbone is configured safely and configured correct for both to keep up with the performance and to make sure it stays secure, the end devices can become the biggest points to enter this backbone. And through those end devices, we are seeing a lot of distributed denial of service attacks with Internet of Things, for example, towards the backbone, towards the really critical applications from DNS to other core functionalities of our network. So given this, we were looking at it as a well, there are the good guys and there are the bad guys, and it looks like this is an arms race. So could we create an artificial arms race to understand, to model this world of good guys versus bad guys, and then use it to improve some of our security related problems. So back in 2018, with my students and collaboration with John from Raytheon, we actually come up with a system, and this was published in TMA 2018. So the idea, as I said, is to create this artificial arms race. But at the same time, we want to try it keep it simple and super simple if possible, and try to understand the different elements of this. So the idea, if it doesn't work in the simplest case, it will never work in the complex case. And from this perspective, we wanted to come up with different elements that we can find in the open source world, and then from there try to use those as the foundation and try to create the artificial arms race. To this end, we looked at the state of the malware on the smartphones. So in general, malware, spreading out and changing very quickly, and this means that it is easily modified. A malware detector may see this problem as I'm trying to show in this figure, where we have the known malware type A and many of these type B, C, and D, and new malware comes. Maybe it's just a little modification to the known malware type A. But obviously, from the detector's perspective, if we have signatures and rules, this will look different, because our signatures and the rules will not really be able to adapt the situation. Yet, this is literally a simple modification on a known type A malware. So it is something of the nature, as we've seen in this animation, you know, the arms race all the time, bringing one upgrade to the existing cyber problems that we are seeing. So how are we going to create that in an artificial case? We thought, can't we have a component that is evolving and represents the evolving malware? And the starting point will be, in this case, a known malware. On the other hand, we are going to have the malware detection system, again, starting from a point to be able to detect these ever-evolving malware. But as the malware evolves, we want that evolution to become a feedback to the detector. And this life cycle arguably can continue forever. Okay, so if we look at the smartphones, open source ones are easier for us to be able to create APIs, download them. So we concentrated in this work on some of the malware that is known on Android. And these have many different categories, and they come in different formats. But I think easiest way of looking at it is maybe a malware is a modified version of a normal app, a benign app, modified in the sense that malware is going to evade or try to evade the detector. That means it has to look very similar to the benign, to the normal, and should have similar permissions as those benign apps. So those are our starting points. On the other hand, the detection, well, the detectors trying to identify the malware by the permissions requested from the app, the code of the app, the features of that code. So we can make the simple detector focus on these kinds of properties. And from this perspective, if we are trying to create this life cycle of evolving malware, giving feedback to the detector, evolving detector, giving feedback to the malware to represent artificial arms race, I think in this kind of a situation, machine learning could be a good match. So we went ahead and looked at different machine learning detectors, which are focusing on simple features of representing apps on the smartphone, Android, and also how they represent it. There are many different features that these detectors are using. In fact, one family of features is the permissions. There are over 100 permissions for our app to request. And state of the art in the literature shows that most of the work uses around 15 to 20 features. So we looked at and tried to focus on the most popular 15 permission features and included those in our detector. We also looked at that detectors are analyzing the features of the app code in terms of the classes using interfaces, their annotations, the methods, whether direct or virtual or abstract, static variables, and so on and so forth. So again, we have chosen 8 of these that most popular seems like in the literature. So that gave us in together 15 permission features, 8 code features, 23 features that the machine learning based detector analyzing. So the whole system, coevolution system, looks something like this. On one hand, we have the detectors. On the other hand, we have the known malwares. The malware evolution actually takes the known malware, and based on how good it can evade or not evade the detector, gets a feedback and evolves the malware, creates the next generation. And the detector, looking at those 23 features I just mentioned, tries to detect the coming malware, and if it cannot detect, then it gets the feedback and tries to evolve itself. To be able to set up this experiment and see how it's going to turn out, this artificial arms race coevolution, we looked at different data sets that are publicly available at the time. So we used 2 malware data sets, one from a university in Germany, and they made it publicly available, Trebin, and the other one was from North Carolina. Again, both of them were making malwares available that are around 2010, 2012. So we used those data sets. We took some samples from them to be able to train this machine learning to start the coevolution. And then we had another 10,000 exemplars from different from the same data sets, but different than the training, to be able to test and validate. Also, at the same time, we get into the so-called wild, use the GetJar website, and it's an app store where we found other malwares and downloaded for testing purposes. Of course, in this coevolution, we have to represent the benign apps as well. For this purpose, we use Google Play and F-Droid, again, very widely used open source app stores. And to start with training purposes, we downloaded 700 apps and then another 300 for validation and started the process. And once we validated, we tested the detectors that are co-evolved during this artificial arms race, and we detected them against machine learning that is not co-evolved. So here you see the complexity of the detector in terms of how many rules it uses to detect. If we don't use coevolution as an artificial arms race, it has 41 rules to be able to detect these malwares, whereas in the artificial arms race, the end result brings down the rule set, so it's a less complex, simpler way of detecting. Number of features out of those 23, if we don't co-evolve, 8 features are useful to be able to detect the malware in the test. And when we co-evolve, we can bring it down to 6 features. But if you look at the precision and recall, precision in terms of the benign apps correctly detecting them. Not that much different between the co-evolved and not co-evolved one. However, in terms of detecting the malware, actually we see the coevolution gets much better compared to the non-coevolution detector. And then we took this co-evolved, the best result detector, and used it on the GetJar open app store. And this is a very well-known app store, but we, millions of downloads a day. However, we only chose 15 for that work as a preliminary test to see how it's going to do. And here is the result. Now what you are seeing here is actually 4 different detectors. One of them is called VirusTotal. I'm not sure how many of you are familiar with this, and I should explain, this is not just one detector. It's a website where you can submit an app, and it has many detectors in the range of 40 to 50, and runs this app through all of them, and then gives you back a result. So what you see here as percentages, how many of VirusTotal detectors actually, what percentage actually correctly detected these 11 apps that we know are for sure malware. And we repeated the process this time with a machine learning algorithm called decision tree. And you can see how it can detect using the same features that I described to you, the 23 features. This is a non-co-evolved detector, and it's equivalent co-evolved. And in this case, what is happening is pretty much all of these detectors detected these malwares found in the wild, be it 11 of them, but you can see that there are many detectors that are under VirusTotal that were not able to detect each one of these malwares. So only 1/3 in the first 2, none in this 4th one. And if you look at this 4th one specifically, actually the 2 machine learning algorithms couldn't detect it either. But arms race, which is the artificially co-evolved one, did manage to detect. But the set is very small. So what we did is actually made a bigger experiment. But before I went there, I just wanted to show you the if we co-evolve the detector out of the 23 features, which ones it uses to be able to detect a malware versus a non-co-evolved one. And there are some similarities, like the read phone state, and there are some differences, as you can see. So in the bigger experiment, after getting these promising results, this time I work with my student Zachary, and this work is published last year in a security workshop. So we are looking at the co-evolved detector that I just presented. So that part is not changed. Now we are comparing it to some other well-known open source detectors. One of these is called assembly line, which is used, which is designed and developed by the Canadian Security Center. The other one is VirusTotal, which I had just presented and be used in our previous work. So, and then we have some new data sets introduced in this extended work. One of them is called Android malware dataset. This is an academic dataset provided by University of South Florida. And as you can see, it is from 2010 to 2016, so newer than the datasets we use in the previous work, and more samples and 71 different categories, families of malware. And then here's another academic data set that is provided by University of New Brunswick. And this time we are looking at malware that is generated between 2015 to 2017. And this data set has 42 4 categories and 42 families of malware. We also had downloaded data sets from VirusShare, the community data set from anonymous donors. These have malwares from 2013 to 2014. And we downloaded all the 35,000 malware samples, but over 10,000 of them were corrupted, and we were not able to decompile them. Okay, here is our experimental setup. We have our training and testing for the coevolution, and as well as for other machine learning based algorithms, and we have assembly line and VirusTotal, and we are trying to get the detection rate and false alarm rate from these systems. What I wanted to show you is on these new data sets that we added, actually it seems like the New Brunswick malware and the virus share malware have totally undetectable samples. So the new malware is becoming more difficult, and VirusTotal detectors couldn't detect some of those samples. And we are looking at now assembly line, and in this case we see that the detection rates are lower than the previous experiments, but at the same time one needs to put out that assembly line not necessarily a detection system, but it's more of an analysis system of the different parts of the malware app and which family it belongs to. So we are not directly comparing maybe apples and apples here. However, it gives us an idea about these 3 new data sets that we introduced, which are publicly available. It gives us an idea that these data sets are challenging data sets for open source systems to be able to analyze and detect. This is a machine learning algorithm which is not co-evolved, which doesn't belong to the artificial arms race, and it seems to do well on the Android malware data set, and has a good model for the non-malware part of the New Brunswick data set. On training, it actually gives some good results with 22% in average increase. So the co-evolved system on the 3 new data sets, when we look at it, Android malware, virus share, actually we got really good results when we looked at our co-evolved detector. For the benign part of the New Brunswick data set, we had pretty good results. I'm just trying to summarize. You see the numbers in the table. And we get an increase in average 12% compared to the, in terms of detection rates, compared to the previous experiments. And the parts that other systems have difficult to detect, basically we had almost 90% detection rate in those cases. So it gives us the promising results we had got in 2018. We actually managed to even did better and improve on them in 2019. So it gives us a good feeling that we are on the right track with the coevolution in creating this artificial coevolution to be able to understand and model what is happening on our networks, applications, and services in the current cyber ecosystem. Quickly, I want to introduce you another work that we did kind of along the same lines, but this time we looked at only the, if you like, evolving the malware part of this coevolution system. So why is this important? Well, if we want to be a step ahead of the bad guys, so to speak, that means, and everything is very quickly changing on our high-speed systems and networks. That means we really cannot sit and wait to see what they are going to do. We need to create an environment, be it artificial, that will give us some idea of what might happen. So given the current COVID-19 pandemic we are living, if I can make some bad analogy, I guess, we don't need to wait till the pandemic happens, but we can maybe find a way to predict these type of things can happen in our cyber world as well. And this is where I think artificially evolving both the good and the bad behavior is important. And especially to improve the good behavior, we really need to be able to understand and use the artificial bad behavior to if you like, train and learn to get better in our cyber defenses. So in this sense, we are looking at evolving return-oriented program evolution with Robbery. So if you, as you can see, it's actually recursive. So I am not sure how many of you are familiar with return-oriented programming, but before I go there, in the good old days, we had buffer overflows, right? And this is one way of attacking. And as we recognized how these attacks happen, we made our operating systems and compilers and so on stronger. And harder to evade. So that means what is happening is now we are talking about systems where buffer overflow attacks are difficult to make, and the code the programs are making sure that permissions are checked and only the part of the code that has a right to write, so to speak, and execute will be able to write and execute to the registers. So Robbery is a system for evolving populations of return-oriented programming change for a target executable. If this can be used by a bad guy, what would happen is the question we wanted to ask. So I don't know, I think old enough to remember the MacGyver from many decades ago. So he would never have a gun, but he would go to a situation, see what is out there, use that to defend the good guys against the bad guys. So this is what we are trying to do. We have a situation where we have maybe an exploitable vulnerability in a target process, and this can be corrupted with using the instruction pointer. So the problem is, though, from the attacker's perspective, they won't be able to write to executable memory, and they won't be able to execute to writable memory. So the old school shellcode attacks, buffer overflow attacks, etc., will not work. But what they can do then is they can reuse the pieces of the memory that are already executable. But from the attacker's perspective, the trick they need to find is rearranging them into something useful. So from defense perspective, if we can predict how they are going to rearrange, we might be able to create signatures against those in our defense system, or we might be able to strengthen our defense system using how the attacker is going to do these rearrangements. So we need to find a way to predict this. All right, before going there, again, just to give an intro in case you are not familiar with the terminology, we are talking about gadgets. These are any chunk of machine code that is already mapped to executable memory, and they allow us to regain control of the instruction pointer after it executes. So keep that in mind. We are now trying to look at generalization of this gadget concept. So we want to find the precise meaning of a return instruction in the, which is not, this is usually architecture dependent, and not all architectures implement the return as a pop into the pointer. So the essential idea we are after is stack control jumps. And we are going to find ways to be able to make use of whatever instruction is available at a given time when a process is running in the memory, and use only those instructions to create chains to be able to achieve the rearranging, if you like, to do our target. Okay, so now we tried this in something called ARM router HTTP daemon, and the version we are using, so to speak, is Tomato RT and 18U HTTPD. So if this is what is running in the memory, and this is the only thing that has a right to execute, write, delete, and etc., basically in one shape or form, if the attacker is on that system, these are the only commands that the attacker will be able to use. Okay, and here you see the different types of commands at the register level, assembly level. The pops are the violet ones, the returns are the greens, source is the blue, and destination are yellow. So as you can see, there is a variety of things, and in a really sketchy way. Could it be used to make an attack? So that's the question we are asking. And the answer we are going to do is by using machine learning to find, to evolve a program that finds a way to rearrange these commands to do something bad. Okay, how are we going to do this? Here is our evolution. So we are going in with a target binary, extracting its gadgets. Then we are going to represent these gadgets in a genetic process and evolve it in our virtual machine to see what kind of rearrangements are coming out and if any of those rearrangements are bad behaviors. So in this case, obviously this search can be quite long. If we say, hey, we are gonna rearrange everything, look at every single permutation. Technically and theoretically, this is not impossible, but we are doing academic research, and the idea is to be able to see quickly if there is something that is useful, and maybe that we can afterwards analyze. So to be able to do that, we had to focus the search a bit. And in this case, we said, okay, what happens if we try to look at if we can make a call. As you can see, the exec v bin/sh, this call. This is what we are trying to get at. Now I want to show you an example of a compiled shell popping rob chain, which actually achieves that. And this is the payload. This is published in Black Hat 2011. So we want to come up with some payloads similar to this, doing this job. Here is on the right-hand side, you see the runtime. And we want to see if any of those commands I showed you in the ARM router HTTP daemon would be able to have instructions to rearrange together as an end result, get here. And it turns out that it does. So I'm not sure how much you can read it, and most probably you cannot. But you have a long set of instructions here. That's what you see. And these are, for your convenience, we arrange them into gadgets. Here is first gadget block. Here is the second gadget block, third, and then so on and so forth. And we see the extended gadgets as well. The whole thing has to be run to make the harm, okay? But all those HTTPD commands can be put together, rearranged together to give this to us. And here, what I want you to pay attention is actually our target is the blue line at the very end. To be able to get there, attacker is rearranging the available instructions in the memory, one after another. Here, the violet ones actually represents the jumps, and the red ones that you see represents the use of the gadgets. Okay, so as you can see, it takes a few jumps and a few gadgets to be able to get where the attacker wants the pointer to get, so to speak. What else we did is, this was funny, I think my student got very interested after doing this, and she said, all right, if we had an HTTP daemon, I don't want to be the bad person. So rather than trying to do other attacks, I want to look at if with that HTTP daemon instructions, can I classify flowers? There's a very well-known data set called IRIS from the machine learning benchmarking data sets archive. So we try to rearrange the HTTP daemon instructions to be able to classify iris flowers. So original data sets has different types of iris flowers. These are the triangles, green, red, pink, as you can see, and squares. This is how the data set looks like. And in the HTTP daemon, we managed to put together the instructions and rearrange them so that we can classify those iris flowers correctly, running HTTP daemon instructions at almost 97% detection rate. So I thought that was something fun to share with you. Okay, throughout this cyber arms race, what did we learn? Are we really able to do artificial evolutions and use them towards prediction so that they can be turned into signatures and improve our cyber defenses and our cyber detectors? If we are using machine learning based defense systems or augment them, the defense systems with machine learning, it becomes more and more data driven. So we learned that actually we can get, by evolving the data, new insight and new knowledge. And something that we need to be paying attention is the representation of the input. And the input could be at many different levels, from BGP traffic to smartphone usage or anything in between, depending on what our focus and objective is. To generalize these evolved solutions, or to test whether they are robust enough, resilient enough, they generalize well, i.e. they manage to adapt, then how are we going to ask those questions and evaluate for them? What does generalization mean for cybersecurity? Some of the dimensions, angles there, will the solutions be as good as they are over time? Will the solutions be as good as they are when we change the location where we use them? This can be the location in terms of the network it is on, the server it is on, or geographical location. And what are the evasion attacks that are done against these type cybersecurity detectors? So these are, I think, what we learned is that these are the important questions that I think we need to pay attention to. And there are interesting behaviors that we can learn and make use of throughout these studies. Also, it is important what we are trying to achieve. Is it a known behavior that we want to recreate? Is it a change in some behavior? Is it something totally new? And is it important to have a confidence, a certainty level in terms of what we are doing and how right or wrong it might be? I think when we are trying to set up artificial arms races to model what might happen or what is happening, one important issue is that, as I said, these artificial evolving arms races takes time to put them together. And if we had infinite time, they could run infinitely. But in our fast-changing high-speed networks, that's not that useful. So that means we have to bring in some a priori information to be able to constrain the search space and get results quicker. And this is in itself very well, but we also need to keep in mind that the more prior information, a priori information that we bring into this kind of systems, the more blind sites we are creating, because those are the parts that prior information we bring in means that we don't need to check out, search for those combinations. Last but not the least, it's always good to start the artificial coevolution, in our experiments at least, from a point, from a known point. Known here means, if I look at networks, known is the ground truth about our networks. You know, what type of traffic we have on it, what kind of protocols running. These are all ground truth. If you take it to the level of, say, traffic and packet, so you have a ground truth about every single packet. Well, in a high-speed network, that is very costly to know every single packet, what's happening, providing labels, defining, in other words, what is known in terms of good and bad, benign and malware. These are costly procedures. So how much ground truth we need to be able to kickstart such an artificial arms race is something to keep in mind. And the deployment environment, where we are going to use this, again, very important. And to my mind, looking at the generalization from these three dimensions, the location, the time, and evasion should always be at the forefront of our experimentation and trials. What is next for us? For my research group and myself, always coming up with a model that is working as a always learning to model the change in our networks, systems, and services. So trying to understand and make the first stab at this ever-changing cycle is my current goal, and also what is next for me. So it's kind of recursive. Thank you very much. And I just want to show you all the great students that I had pleasure to work with, and without them, none of this work could have been done. Thank you.
Dr. Heywood, thank you very much for this great talk. And thank you for all what you do for the field, really. And I know that a lot of students in your lab see you as a role model, especially with the women, right? Women in computer science. So I thank you again for all what you do. I don't know if you have a few minutes, if anyone of the participants would like to have some questions.
Sure, I would be happy to answer if there are any questions.
Sure. I mean, it will be a pleasure to continue if you can attend the remaining of this workshop, and if you have any questions for Dr. Heywood, feel free to reach out to her through email or later on. So we'll continue basically. Dr. Heywood, thank you again, and for sure, I mean, if you have any questions also for your students in terms of the labs, please feel free to reach out anytime.
Thank you. Thank you, everyone, for inviting me. And it was a pleasure and honor to be with all of you. And please feel free to email me if you have any questions, and I'll be continuing to listen into the workshop.
Thank you. Thank you. So I'll terminate.